many space agencies all over the world, many NASA centers, commercial companies. There's only one of them that sends spacecraft to all the 8 planets in the solar system and various moons. Which one is that? Of course, JPL, right? That's what we are extremely proud of. However, there are only like 3 worlds that humans, not just JPL, as entire civilization, sent the complex robotic capabilities. There's Moon, Venus, and Mars. And what I'm going to argue today is that we would need a new paradigm, which I call robotic exploration 3.0, but whatever you call it, to answer some of the most profound questions of humankind. For example, are we alone? Right? Life on Earth, are in 4 billion years of solitude, meaning that we don't know yet if the cosmos is full of life and we have not just met others yet, or the universe is just, the lifeless extent of space and time only with one single pale blue dot. We don't know. We want to know. That's why we go to space. So we've been exploring space like 60, 70 years up to now. The way we explored space changed over time. So let's look back quickly. What we call exploration 1.0, that's basically a decade that leads up to the Apollo landing in like late 50s to 60s. During this decade, we sent like 20 missions to the moon, out of which only 8 were successful. Right? So the exploration 1.0 was basically a fast-paced trial and errors. And that was it. But, trial and error was actually a very efficient way of learning new capabilities, as you know, right? And that was possible for the moon. That was a completely valid way to do for the moon because it's just 3 days away. A launch opportunity comes up every month, basically, right? However, this way does not work for Mars, simply because it takes 6 to 7 months to get there, and the launch window opens up once in every 26 months, right? So you cannot try and fail every month for Mars. That's why we employed a different approach, which we call exploration 2.0. In the past 3 decades, we sent 14 spacecraft to Mars, out of which 11 were successful. So we were more cautious than what we used to be for the moon. But being cautious is not really the point of the 2.0 model. The real point is that we incrementally sophisticated the robotic capabilities through the series of missions by building upon the knowledge that we obtained from the previous missions. Right. For example, I wrote the flight software of the autonomous driving for Mars. That was one of my, one of the things I did that I'm most proud of. And was enormously successful. The way we've been successful was at least partially to build upon the intricate environmental knowledge that we already had from prior missions. Right? For example, when we validated the sleep robustness of this new algorithm, we used all the drive data from prior rover, Curiosity. And when we evaluated the drive performance, we used the high-resolution satellite images and run Monte Carlo simulation over and over. So, again, the point here is that as we've been successful on Mars, the way we've been successful was to build upon the existing knowledge about the environment. So conceptually, this is how, this 2.0 paradigm works, right? Initially, you don't know anything about the environment. So the environmental uncertainty is very high. Therefore, you start with low risk, low complexity mission, maybe just orbiter, right? To learn a little bit about the surface environment. And then, using that knowledge, you send a simple robotic mission to the surface to learn more about the environment. Now, once you know enough about the surface environment, you use that knowledge to design a complex robotic mission that works specifically to that environment. That was Curiosity, Perseverance, or Mars sample return that we are doing right now. And this robotic exploration 2.0 style paradigm has been enormously successful for Mars. And I'm so proud to be a part of it. But we must ask this question: can we stick to this paradigm to explore the destinations that are far more challenging than the surface of Mars, right? And where are those destinations, right? Where are the best places to look for, life specifically? It turned out to be the icy moons of gas giants, Jupiter, Saturn, Uranus. In other solar systems, many moons are actually made of ice. And some of them, such as Europa, Titan, Ganymede, some moons have ocean below the ice. It's a liquid water ocean, which is fascinating. This moon is particularly interesting. It's called Enceladus. It's a tiny moon of Saturn. When Cassini spacecraft went to Enceladus, it finds something very unexpected. Geysers, the gigantic geysers that turned out to be, or likely connected to, the subsurface global ocean. And there are 4 gigantic crevasses running through the South Pole. Through the crevasse, this liquid ocean water comes out and sprays out to the moon, ejected to space, and forming one of the rings of Saturn, right? Which is amazing. And by the way, on Earth, wherever we find water, we find life, right? So, is there something living in there? That's what scientists are wondering. And if there is, what are they, right? It's microbes or potentially, giant octopi or, bluefin tuna or I don't know, right? We want to know. So we thought, can we send a little robot through this crevasse to the ocean to investigate if there's any life over there? Then again, we have to ask the question: can we use 2.0 style exploration to do such a mission? The answer is a clear no for 3 reasons. One is that the orbital reconnaissance of the subsurface environment from orbit is impossible, right? And 2, to get to the outer solar system destinations, it typically takes 10 years or more. So if you want to send 10 missions sequentially, that could be easily a century. And most importantly, it's not just about one planet, right? It's not just about Mars. There are many worlds that we want to explore. So we wish to be able to send like 10 missions to each of them. We don't have time and resources to do so. So we somehow have to figure out a new paradigm that enables us to explore such a highly unknown environment in one shot, right? So that's the problem that we are facing. And our answer to that problem is this robot called EELS, Exobiology Extant Life Surveyor. It's a snake robot. Looks cool, right? But the point of this robot is not just being a snake. The point of this robot is actually being adaptive. Compared to conventional space robots like, Mars rovers, rovers, although it has been enormously successful, it's not very adaptive, meaning that its behaviors are designed based on the knowledges that we already have about the environment, and it's fixed before the launch. As opposed to an adaptive robot like EELS, it is adaptive by design, meaning that its behaviors can be learned from its own experience and evolve during the mission. And by using such an adaptive robot, we think we can enable a new paradigm of exploration, which we call Exploration 3.0, which is a one-shot exploration using high-level adaptivity. It goes like this. Again, you start with an environment with little to no knowledges, right? But you send this adaptive robot directly into that environment. But because environmental uncertainty is so high, risk is very high, so you start with low complexity tasks. Maybe raise his head, look around, that's it, to figure out about the environment. Once you learn a little bit about the environment, now you have information to exploit. You adapt your behavior to that environment to do some medium complexity task. Maybe slowly moving around, that's it. But by doing so, you learn more about the environment. Once you learn enough about the environment, now you're going to adapt again to perform highly complex tasks. Right? Point here is that instead of sending a sequence of missions, by designing, based on previous missions, by sending one robot that is highly adaptive, you can modulate this risk behavioral complexity trade-off in situ, right? And hence you don't have to depend on sequential missions that are going to take a century. Okay, so here's how we think the future Enceladus mission would look like. This robot gonna land on it and slither on the surface, find the most promising entrance to the crevasse, and get in there. And it learns about the environment. It figures out what's the best way to go down the vent. Maybe taking the spiral form, maybe taking a pencil form like that to go through the narrowest part. Eventually get to the ocean, collect the sample, look for the signs of life. If it finds life, we're going to collect the Nobel Prize. Okay, so beyond here, I know the time is limited. I have too many things to talk about. I have 3 topics from which I'm going to let you choose 2 of them. Clear, all right? First one, that is more about EELS. Second one, that's more about on Mars. Half of this Mars topic is about Exploration 2.0, how we implemented and made it work to drive autonomy on Mars. But the other half is how to adapt it to 3.0 paradigm by using machine learning. The third topic, that's more theoretical, that's risk-aware planning, somewhat similar to what Marco and his students are doing. But this is a central concept for enabling 3.0 paradigm. Okay, you're going to have 2 choices. Who wants to hear about EELS? Okay, let's not count. Let's see, if there are obvious 2 choices. Who want to hear about Mars? Okay, want to hear about risk-aware? Okay, it's pretty close. Okay, so let's vote for Mars and risk-aware once again. Mars. 1, 2, 3, 4. Yeah, keep your hands. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, risk-aware. I think this is the winner. Okay, let's go for the EELS and risk-aware things. Awesome. So EELS, we do not view this as a robot. We view this as a system made of software, hardware, instrument, and ground system. It has autonomy. Neo-autonomy is the name that we put it. It's a package, basically, package that includes low-level locomotion control, force feedback control, to path and motion planning, and higher-level risk-aware planning. Locomotion, it has 30 to 48 DOF. You can have more to make it versatile. That's the key for adaptation. I will talk more about it. As the sensor head has LiDAR cameras, IMU, but we can have different kind of sensors depending on the mission. Active skin propulsion has a rotating screws on the side. Again, I will talk more about it in the next slides. And the robot is modularized and completely independent from each other. So you can add payloads on anywhere in the body. And for now, we use tether, but we can build a version without tether. Okay, so first I'm going to talk a little bit about individual technologies without going too deep into it. We have papers, so you can go to it if you're interested. Hardware-wise, we developed the actuators in-house. It's an ultra-high torque density outrunner motor, has 400 Nm output. One of the highest torque density electric motor that's available on the market, actually. So it is not just strong. It has integrated strain-based torque sensing, which is crucial for proprioceptive control. And we also developed distributed motor control avionics. Active skin propulsion, that is the central mechanism of this EELS robot. The robot has the rotating screws on the side. The thread goes to different directions, all the alternating directions. So if you rotate them to the alternating directions, this pushes the robot forward or backward, right? If you take a non-straight form and then rotate it in a coordinated way, you can go to the side. So it provides omnidirectional mobility. Plus, the point is that this is a nice way to decouple, the locomotion from shape control to make the control problem easier. This is not from us. This is from Mike Webb at UCSD, but he experimented the active skin propulsion for submerged mobility. So the robot can be amphibious. If you look inside each module, it's full of the mechanisms. For each module has 3 to 4 DOFs, 2 degrees of freedoms between joints, bending, and the twisting. In our version 1 robot, the 2 screws at each module is actuated in a coupled way in the different directions. In our 2.1 robot is actuated independently. So each section is full of actuators and the motor avionics here. Okay, so let's talk about control. Proprioceptive control is one of our key elements. This guy is climbing the rock. That doesn't look special. He has muscle. But one notable thing about this guy is that this guy is blind, right? So he does not use any visual feedback. He only relies on proprioceptive information to climb up this cliff. That's amazing. But actually, all of you guys are doing this, right? When you look at your smartphone and walk like this, right? You don't rely much on your visual information. And this is something that maybe underrated in the robotics. We do use visual information, but when you are walking, for example, you rely more on the haptic feedback from your bottom of the foot, right? So you can walk with your smartphone, right, like this. But if you are cut off from your haptic sensing from the bottom of the feet, probably you cannot walk in a stable manner, right? So that's what humans and animals do, and that's what robots should do when you want to do a complex task like moving vertically between walls. Exteroceptive perception, of course, we have LiDAR, camera, weight, and SLAM. That doesn't sound very special. One unique thing, though, that we did is that we created a version of SLAM from ICP. We modeled the uncertainty that involves in estimation, so that the planner and controller downwards can use the information that is involved in the in SLAM, which we published in IWAS last year. And risk-aware autonomy, which I'm going to talk more in the later section. But it's about making judgment, modulating your behavior based on the level of risks. And we did not a full deployment. We did preliminary deployment on the robot and testing in the lab to concurrently optimize the route in continuous space and discrete actions. And although we do not rely machine learning for perception and planning, but we experimented using reinforcement learning for acquiring new gait patterns. So one particular thing we tried, it's kind of merger of model free and model based. We learned, we run thousands of we run thousands of estimations in Isaac Zim and got the gait patterns which we mapped to central pattern generator to implement in a real robot. In that way, you can remove some randomness and find out a stable controller while exploring in the parameter space through the reinforcement learning. So here are the somehow the movie is not working, but yeah, we transferred this gate to the real robot. Okay, we prototyped 5 EELS robots. These two are the big ones, 1.0 and 1.5. That are the ones that we brought to a glacier for field testing. We are working on these small variants, garden EELS, mini EELS, and then 2.0, that's our ultimate robot, which we haven't completed yet. So, since our goal is to demonstrate its adaptivity, so we field hardened the robot over a wide range of environment. We started from Pasadena ice rink. That was an easy one. We rented out from 10 p.m. to 5 a.m. We tested on the flat ice, which was easy, And then we tested the robot extensively at JPL's Mars yard, moving on granular sand, moving over a rock, climbing up a sandy slope. We brought the robot to Snow Mountains, Table Mountain Observatory, and actually Big Bear Ski Resort. Here you go. We tested side-winding gate for climbing up the slope. It climbed up 35 degrees of snow-covered slope. We went to a glacier for testing our sensor head in 2022. We tested a lot in the lab environment, of course. This one particular is testing the risk-aware autonomy, raising its head, look around to reduce the uncertainty. As I said, we transferred the gait learned from sim using RL to real. Here we retrofitted the gripper at the tail to turn it to a mobile motivator. And then, of course, vertical mobility, that was the most difficult one. So we erected ice walls in the walking freezer, and this is a version 1.5 robot. This robot expands its arms to push the ice walls against each other to support its own weight. Look at this guy's face. Wow! That was the moment when the robot made the first successful, upward vertical motion in the ice chamber, and we were so happy. This is my favorite demonstration of versatility. On the left, this is Opportunity rover on Mars. Rover is great, but it only has a single locomotion mode, right? So when it got stuck in sand, the only thing it could do is to keep spinning the wheels until it could get out. It took like 30 or 40 sols until you get out. As opposed to EELS, which is versatile, has many modes of locomotion. So when it got stuck in sand in the Mars yard, what it did was to switch to a different gate, side-winding gate, to roll aside and easily escape from the sand trap. Right? That's the power of versatility, having multiple modality of locomotion. Our final field test took place at Athabasca Glacier in Canada. That was last September 2023. We went there for 3 weeks with a team of 30 or 40, quite big team, spending 3 weeks. That was a very interesting, this is a fascinating place, by the way. Our schedule was fully packed. No Saturday, Sundays. It almost looked like a space mission. We set up a base camp. We identified a few test sites. Then the first tests was the surface mobility tests. We have 5 sets of tests at different locations with different conditions. Here are some movies. This one in particular was when the EELS 1.0 robot went in and went out semi-autonomously to the about 2-meter deep ice channel. And we also tested the various kinds of locomotion modes, like side-winding for climbing up the icy slope. But the real reason we went to the glacier is this. It's called Mulan. It looks like crevasse, but curved out by flowing water. It's typically 20, 30 meters deep. It's beautiful. I went down to one of them. It's an amazing place. So we tested. We used our version 1.5 robot using 3 of these Mulans with various setups. This is a typical test setup. This is this dangerous 20, 30 meter deep ice. You guys have to gear up, wear crampons, the harnesses, roped, in order not to fall into those crevasses. We set up the test rig to place the robot into the Mulan. And all the setups, generators, EGSEs, and the operation table over there. And then, this is how the test went. We placed the rover by winching down from the top into the Mulan. Once it's in place, the robot expands its both arms to push the walls against each other and make anchor to support its own weight. And then it used its side screws to move vertically up and down, right? We made 1.5 meter fully autonomous vertical motion multiple times. And I believe it's the first time that the robot of this size made the vertical mobility successfully in a natural opening like that. And this is how we celebrate it. After like many weeks of exhausting tests. I think you guys know this kind of moment, right? Okay. Our next step, we don't know yet, but we hope to test our robot on the moon before sending it to Enceladus. We'll see. Hopefully that's going to happen sometime soon. I didn't go deep into the technologies, individual technologies, but we have a bunch of publications. So, please take a look if you are interested, or just let me know. This is our amazing team. In total, I think 50 or 60 people got involved over the span of the projects. It's totally up, thanks to these guys to make it work. Okay, so let's jump into the risk-aware planning with a lot of mathematics. Okay, so everywhere in the real-world problem, there is risk versus performance trades, right? When you land on Mars, when you plan your landing site, there's a requirement that all the landing safety constraints has to be satisfied over the 3 sigma landing ellipse, which represents 99% confidence. When you want to send a spacecraft to a world that is potentially habitable or inhabited, there's a cost power regression saying that the probability of biological contamination must be less than 1 in 10,000. In the UK, the nuclear regulation says that the risk to the neighborhood has to be limited to 1 in 1 million per year. But the point I'll make here is that, one, you cannot have zero risk solutions. You have to trade between the level of risk and what you can get. And two, in many real-world examples, this risk is specified by chance. Why? Maybe it's because it's intuitive. Maybe it's human understandable. So let's put it in mathematical formulation. Say, there are n safety constraints, g1 to gn of x that must be below 0. And here's the problem you got to solve. With generalization. You want to minimize some cost function, the function of some random variable x, with the constraints that the probability that one or more of the safety constraint is violated must be limited to some small number delta. This is the upper bound of your risk of failure, which is called joint chance constraint. So this joint chance constraint is typically non-convex, non-linear. It's not easy to handle. So let's use some mathematical trick. This is a quite simple mathematical trick. But still, this is a paper from 16 years ago, still one of my best cited paper. A simple trick to decompose the joint chance constraint into a more manageable form. Bose inequality is simply saying that the probability of A or B is less than probability A plus probability B, right? By using that, you can decompose the joint chance constraint into bunch of individual chance constraints, upper bounded by small delta, plus additional linear constraint that the sum of the small delta has to be bounded by, big delta. Easy, right? With some level of the conservatism. Now, how to convexify it, that's up to your specific problem. So let's look at the easiest example, which is linear Gaussian case. Right? Say, your function g of x is affine, and x is Gaussian distributed. Then, this chance constraint is written in a deterministic form like this, using Gaussian CDF. The function looks like that. If you only look at this portion, which is the chance below 0.5, 50%, then it's convex, right? So, this problem is convex if your risk bound is less than 50%, which is not a super demanding assumption, right? You don't typically want to take more than 50% risk, right? So it's usually convex. In general, if Gx is convex, if your distribution is bell-shaped, if not Gaussian, and if your risk bound is quite small, typically it's convex. You can find a way to parameterize and convexify it. Okay, so this is just a mathematical trick, but there's an interesting interpretation of this mathematical trick, which is risk allocation. This is saying that your total individual risk has to be bounded by, this large delta. So you can view this total risk as a resource, right, that you can spend to get to your goal. And this risk has to be distributed over constraints, over time, over different places. So if you want to, go from, start to the goal, there must be an optimal allocation of this risk totaling to large delta, because the sensitivity from risk to cost is different from constraint to constraint, right? So this is pretty much like a resource allocation problem. Now, this problem gets even more interesting if there are multiple agents, right? So let's say there are, a few agents have different sets of the state variables, cost functions, and safety functions, okay? And your problem is that you want to minimize the total cost with a joint chance constraint, saying that all the agents want to satisfy all the safety constraints for a certain probability. You use the same mathematical trick using Boolean inequality to turn it to individual chance constraint plus some additional form. Then this happened to be a decomposable form, so apply dual decomposition, right? So now your primal problem has this Lagrange multiplier over there, which is solved by each agent, can be solved in a distributed manner. It is totally decomposed. And your dual is just to make sure that your, this delta is totaling to large delta. Now, again, this is just a mathematical trick, but there's an interesting interpretation with the market-based interpretation. This Lagrange multiplier lambda is a shadow price, interpretation is a the price of risk. If you want to take 1% risk, this is the price you have to pay, right? And the small delta, that's the risk that each agent want to take. That's a demand for risk from each agent. And this large delta, this is the total amount of risk that you supply to the market, right? And then the optimization goes like, in economics. This is something that you learned in the first class of your microeconomics class, if you take it, right? Economists has a weird habit of putting the independent variable on the vertical axis, but don't worry about it. So, you have a curve, demand curve, right? If the price is high, your demand is low. If the price is low, the demand is high, of course. So, again, each agent has different sensitivity to risk, so they have different demand curve. The market, your dual problem, sets the price for risk. If there is excess supply, you're gonna lower the price, just like in the reward market, and collect the demand from each agent again. If your total demand for risk is more than the supply, then you raise the price until you get to equilibrium. Practically, it's just optimization, zero findings, so you can solve with bisection method quickly. But in economics, it's called tattooment, modeling how the price moves up and down to look for equilibrium. And in this particular problem, you can prove that your risk allocation is globally optimal at the equilibrium when the total demand equilibrates with the supply. So some experiments in simulation with 16 agents. Great thing about this dual decomposition is that the dual problem only has one variable. Why? Because we are talking about joint chance constraint. So joint chance constraint is a curse for primal problem because there's a lot of couplings, but it's a blessing for dual, right? So you only have one dual variable, which is optimized, centralized manner, and all the primal problem is distributed, so it's very scalable. It converges pretty quick. Duality gap goes quickly to 0-ish. And scalability-wise, if you have centralized, then it scales pretty bad in almost exponential, but this dual decomposition-based risk allocation scales very well for a large number of agents. Okay, so let's go to something more practical, maybe. This is the work that I did with Marco, actually, like more than 10 years ago, I guess. Yeah, it's a long time. Mars rover landing and driving is a good example of a sequential decision-making over very different domains. When you find the landing site, it's a problem of placing this probability distribution, right? The landing ellipse optimally to balance the risk and proximity to your science interest. When it lands, we are not doing much autonomy, a little bit actually, but it's a online optimization to find safe enough landing site. But again, not to go too far from the original landing site unless you're going to run out of fuel. And of course, once you land on the surface, you have to plan your path to get to your scientifically interesting places without taking too much risk. So each step is a decision making under uncertainty. And then, for now, we optimize or plan each step in separation. But if you co-optimize, you can be better off. So that's the idea. Okay, I have to go further. Let's skip ahead. We formulated in dynamic programming, you have some dynamics, control constraint, and terminal cost, one-stage cost, and state constraint saying that you should not get into this obstacle, right? So the formulation is that you want to minimize your expected cost, the addition of your terminal cost plus step costs, your chance constraint, meaning that the likelihood of staying within this feasible space for all the time steps has to be more than 1 minus delta. Now, the approach is to solve the dual. Again, joint chance constraint is complex in primal form, but it's a blessing if you look at the dual form. So you look at the dual, but before dualizing it, you need a little bit of massaging. So you define this indicator function. It is 1 if it hits obstacle. Then this probability constraint can be rewritten by the expectation over I. Then you can dualize. The Lagrangian is simply the addition of the step cost plus this indicator function multiplied by the Lagrangian multiplier. So your dual optimization problem looks like this, right? Your inner optimization is unconstrained optimization. So you can solve with whatever algorithm you like. And then the outer loop, that's the dual optimization. But again, it's joint chance constraint, only you have one dual variable, so it can be solved quickly with the bisection search or something. And there's, again, intuitive understanding of this dual form. Your dual variable, Lagrange multiplier, is the penalty, right, of taking a risk. Or you can say it as a price. Similar to this market-based interpretation, right? If your penalty is too low, your primal problem takes too much risk. If the penalty is too low, right, it's too conservative. So you search between them. It's zero finding. So you can again solve by by bisection method to quickly get to the optimal, like this. So good news, dual converges exponentially. and only takes like tens of iterations, which is great. And more importantly, the dual does not grow with problem size. It's awesome. Cut off?
Pretty much.
Okay, all right, so let's go all the way. I'm going to skip. If you look at the randomized mixed policy, randomized decision making, that you can convexify your problem. That's another thing. So, yeah, I'll skip it. But the bottom line is that in chance constrained non-convex problem, you can better off by choosing your action randomly. But yeah, take a look at my paper. Okay, so let's go all over. Sorry for rush. We did some EELS. Okay, I think I needed 4 more hours. Okay, but anyways, I outlined about the progression about space exploration paradigm, and we do need adaptive paradigm to enable one-shot exploration. The key is how to modulate your behaviors based on risk. And then, to wrap up, EELS is a versatile, intelligent robot diving into uncertainty, enabling 3.0 paradigm. We prototyped the hardware and software. We tested in a glacier. With Scoville planning-wise, we presented a few mathematical tricks to convexifying and then solving the problem in an interesting way. Okay, thank you so much. Sorry for the rush.
All right, so I think we have time for just a couple of questions.
Yeah.
But, we're going to have pizza time later, so you have ample time to ask if you have any questions like that. All right, so any questions? Yes.
Yeah, thank you for the talk. One question I'm really interested in is in the mathematical development of those chance constraints or stochastic optimal control, the de facto standard is assuming Gaussian or those kind of clean distributions, and the most environment is non-Gaussian. So usually there's a deviation from your math development in the real mission. As a PI of EELS, do you face such a something some challenges that you cannot solve with those clean math tricks, and then you kind of need to do those engineering issues?
Yes. Yeah. Thanks for asking that. Honestly, there's a huge gap between what theory can provide and what the practical situations. For one thing, your distribution or your model is not that mathematically favorable form. Sometimes you don't even have a distribution. I don't have a straight answer to it, but there are a few ways to at least partially approach to this one. There are multiple works. For example, decomposing the distribution into multiple modes. Something like the Taylor series decomposition to parameterize and expand into a series of different distributions to handle it without resorting to sampling based. And there are a bunch of nonlinear techniques that you can use over there. So that's one step closer to it. But beyond that, it's an open question. What we did on EELS, at least, is that we implemented the co-optimization of the path planning and the action planning. And the uncertainty-wise, we employed a conservative approximation. That's a good start, maybe. And then as you sharpen your pencil, right, by enabling to treat more complex problem, you can reduce this conservative bound.
Mm-hmm. Thank you so much.
Yeah.
One last questions. Yep.
Thank you for the talk. Just wondering about the form factor of the snake-shaped robot. I was wondering whether from day 0 you were sure about the snake-like robot to build for this adaptive strategy, or whether there were other alternatives alternative designs, especially like form factors. For example, you could choose lagged wheel hybrid systems, or maybe like a big gigantic wheel that can change the shape, something like that. So I was just curious whether you had alternatives, and then what was the pros and cons, and how you ended with choosing this snake-shaped robot.
Okay, yeah, I appreciate the question. So yes, we. So first of all, the point of that project was actually not being snake. Snake is one way of making a robot versatile, right? There are many other shapes, maybe spider, maybe legged robot, whatever. So we are not claiming that snake is the best way to solve that problem. It could be a way, but there are reasons behind we chose that configuration, right? Mostly because we don't have the knowledge about how wide the vent is. Could be 10 centimeters, could be meters, could be even more, right? So what's the form of the robot that can adapt to the widest possible possibilities, right? And our answer was snake. But beyond that, there are many other robotic decision-making processes, right? About designs. We did a lot of iterations, and that's a reality of the. We run our project as an agile process. We iterated, particularly for the 1.5 version robot for vertical mobility. We made subtle changes in hardware almost every month. Like in the month leading up to adding the heaters to the screws, changing the configurations. So what's the takeaway? It's really hard, right, to optimize the robot's hardware, software before you actually test it. For one thing, that's the way, that's the reason that we emphasize the adaptivity. But for other things, when it comes to running the real project, right, you got to be adaptive in your project management also to be able to quickly change your design, both hardware and software. So that's the way that we succeeded in the vertical mobility demo. So thanks for asking.
All right. Thank you.
Okay, thank you.